So, hi everyone. We'll be starting with the summary of week 10's lectures. Uh, Beginning with it. Okay, I think you had some intro with the branch instructions or instructions in general of ARM uh, processor. For that, okay, so you're able to see the screen, right?
Yes, it is visible.
Okay. So, operating modes, I think we have already discussed. But one thing that was left that I want to lay stress on is that. Okay, so of all the operating modes, one of the characterization was on basis of the privileged and non-privileged modes, right? Only one of your system mode, I think that's what it was called. Yeah, in which most of the time your processor works in. That is the non-privileged mode. All others are your privileged modes. That's one thing. And you can modify your CPSR in only the privileged modes, not in the your normal mode. That's what I wanted to say about operating modes. Then branch instructions. So all of the branches, as you must be knowing by now, are relative to your program counter. And you can go from you can jump through these branch instructions relative to program counter by plus or minus 32 MBs, right? So 32, should I write it? Mhm. Okay. Since people have not joined, so can jump uh, up to plus minus 32 MB relative to your program counter. Okay. Then you have your standard branch condition, which is unconditional. You have conditional instructions in which you can have branching if like you can have the conditions as per your flag registers. If there's a zero flag raised or if it's not raised, if there's a carry, if there's no carry in the previous operation, results of the previous operation, then accordingly you can have your conditional branch instructions. Then these two branch instructions, BL and BLX. BL for the branch with link, uh, in which it's like your subroutine, in which the address of your next instruction, which is PC plus 4, is saved to your link register. Why PC plus 4? Why not PC plus 1? Any idea?
Hello, am I audible?
Yeah. Yeah.
Because the MSB 4 bits of each instructions are means reserved to hold 16 condition codes. That's why.
Basically, your memory is
Six,
divided into these 4 by 4
4. Yeah.
four kind of registers, right? So your one instruction, which is 32-bit long, is going to be saved as four parts, 8, 8, 8, and 8. So one instruction of 32 bits has these four locations, and then next will be stored at if your current location is PC, then next instruction will be stored at PC plus 4, because the complete instruction will take four places. All right. So for this branch with link instruction, your PC plus 4 will be stored into the link register, and you can have conditions also for this branch with link uh, instruction, same as the other conditional branch instructions. Then you have this BLX instruction in which okay, I think I it should be one. Okay. What it does is it's used to invoke the thumb subroutine. All right. So when you write this instruction, when this instruction is executed, this T flag goes to one, and which means your subroutine will be a thumb subroutine. That's one. Then you have swap instruction. How does swap instruction? Okay. So before that, this format, I think it's clear, right? Format of the branch instruction.
You please tell, repeat,
Just
please.
yeah.
Yeah, this one.
Okay. So condition is whatever condition you require in your branch condition, that will be stored from these 28 bits to 31, 31 to 28. Then this 101 remains as it is. L bit, this 24 bit number 24 is can be 0 or 1, and depends on whether you have a branch, normal branch, or a branch with link. Okay, so if it's 0, then it's normal branch. If it's 1, then you have branch with link. And then this offset is for your total range, how much you want to jump. Like this is the offset. This is the maximum offset, which means maximum jump that am I writing? Maximum offset, and this is the maximum you can jump, right? Plus 32 MB of your PC value or minus 32 MB. So, whatever, by however value you want to jump, that comes to from 0 to 23 bits. Why 0 to 23 bit? Because 32 MB equals to 2 to power. Anyone? So I did this in class also.
5.
Okay. So, total is plus 32 to minus 32, which means uh, total range of jump is 64 MB, and 64, which is equal to 64 is 2 to power 6, MB is 2 to power 20, which gives us 2 to power 26, which means we require 26 bits to cover this range of addresses, right? But since because we have the memory stored as these four parts, all the instructions, all the memory spaces are divided in this aligned in these four parts, four columns, or four whatever you like to call it. So for every instruction, or for every starting of that memory location you want to locate, the first two bits, like D0 and D1, they are always going to be 0, because always the address is going to be multiple of 4. For multiple of 4, you know that this LSB and the next bit are always going to be 0, 0. So this boils down our required bits to 24. because D0 and D1 are always 0, 0. Okay, did you get it?
Yeah.
So because all every time your address will in your address of instruction, D0 and D1 are always going to be 0. So number of bits that you require to mention your or specify your jump is 24 bits. So these 0 to 23 are going to give the are sufficient to specify the offset that you want for your branch instruction. Okay.
Yeah.
So for this we have swap instruction. For swap instruction, you need to have this RM. Okay, so what is swap? You know that two values are swapping. So which two values are swapping? First of all,
Swap between register and memory.
sorry, I didn't get you.
Swap between two registers,
Two
or the
registers.
value of register and memory.
Your memory is your register because ARM works with registers only, right?
Yeah, 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 yeah.
Right. So all the instructions are going to be
Register
executed
based.
on the registers only.
Register.
So yeah,
Yeah, yeah.
register is your memory.
Mm.
So swap instruction swaps the values of two registers, right?
Yeah.
So
Yeah.
for actual swapping to take place, you have to get these RM and RN equal to, I mean, the same registers, so that the if let's say these RM and RN are equal to R1 and RD is equal to R2. So this instruction will do what? Swap the contents of these R1 and R2. Okay. So, sir discussed this in class also, but let's say you have some memory location, some register, and okay, so taken R1. Okay, this was just for example. So let's say you have some R1 register and there is some temporary location that you're using. This is also a register, okay? Let's say this is R2. So what will happen is, first of all, your contents of this memory is R2. Contents of this memory is going to be stored to some temporary register. This is the first thing that happens. Then once you've stored the contents of your memory somewhere, this place is free, so you can use this place to fill up with the contents of the one of the registers that you
Yeah.
intend to swap with. Once you have stored contents of this register, this is free, which means the original value of this memory location can now be transferred to this. So, all right,
Yeah. Using third variable. Swap using third
using,
variable.
yes, yes. So this is done internally. So this one instruction will do all of this. If this instruction was not present, basically you'd have to use three registers and do the three processes. But with this one instruction, you can do the swapping. Okay. So after this, we have modifying the status register. Okay, so modifying your status register, which is CPSR, is only possible. Oh, Okay, so yeah, as I mentioned earlier also, it is possible in privilege modes only, and is indirectly only indirectly you can modify the CPSR with the MSR and MRS instructions. One example is given here. So what however you want to modify it, you fill register. Okay, this can be done through yeah, you put the value in your register, and then MSR means it is going to move the contents of R5. This will do what? CPSR will get the contents of R5, and this can be done in your privilege mode only. All right.
Yeah.
Next. Okay. And instructions, pros and cons. As you already know, thumb is a very power efficient mode. Yeah, and the code is denser than ARM code. And what else? Oh, okay. Think of it. So whenever you store your data in 32-bit forms, your ARM instruction will do better because thumb instruction requires decompressing of these 32-bit instructions into uh, 32-bit data to your 16-bit data form, right? So whenever you store your data in 32-bit form, your ARM instructions will do better. Whenever you store your data in forms of 16-bit, your thumb will do better because thumb has 16-bit instructions only. One more point I'm missing. Uh, and once you move back to thumb, you get your push and pop instruction back, but that's not a major point. The thing is, for decompressing, your thumb requires some time, right? So performance-wise, thumb won't be that better, but ARM instructions will be better, obviously, when you're storing in 32-bit size, right? So yeah, power-wise, your thumb instructions are better. Lost my notes from this.
Yeah, thumb
Yeah.
codes are
Y-
thumb codes
Yes.
uses
Okay.
30% less power than ARM code.
Yeah. So thumb uses 30% less power, and yeah, so that's what I was saying. That memory is when organized in 32-bit words, the ARM does better. And when you're organizing your memory in 16 bits, your thumb will do better by 45%, which is huge. And it uses less power. So whenever you want power efficiency, you'll use thumb instructions. Whenever you want yeah, performance to be best, you'll use ARM instructions. That's that. And then we have exceptions. So exceptions you can have exceptions from software, your undefined instructions, memory abort. These are your some of your operating modes only. Then if there's a failure in data fetching, then that can be an exception. Or you can have exceptions from your reset FIQ or IRQs, and whenever the exception occurs, your processor will move to the privilege modes or the privilege modes that were mentioned earlier last week. So what happens is, should I write this? Just a minute. Okay. So When exception occurs, what should happen? Like exception is just like yeah, interrupts, right? So what should happen first? What used to happen when interrupts occurred? Either your processor is free or it's not free. Let's just assume that the processor is free to uh, invoke the ISR. So what will happen first?
Halt the current instruction, like it will save the program
It will
current.
complete the current instruction, execution of current instruction. After that, it will go to ISR of the ISR. Yeah.
corresponding ISR address.
Yes. Yes. So before going to the ISR, there is one thing that happens.
It will store the returning address to somewhere.
Yes. Yes. So it will store somewhere where for the for the ARM processor
It will store in link register.
link register. Okay. So first of all, what will happen is value of PC plus 4 will be stored in your link register, which is R14, right? What will happen next? One more thing before going to ISR.
The current CPSR copied into SPSR.
Yes. So your CPSR, because it might be used in your ISR, so you copy it to SPSR. Then your other interrupts are disabled, right?
Yeah,
Disable other interrupts. Then there's one different thing that happens, I mean, differently from the processes that we have done. If you can have a fast interrupt also, right? From interrupt from fast interrupt mode. So what happens is, let's say if this interrupt is from FIQ only, then you disable FIQ because FIQ means interrupt from FIQ means that's the highest priority, right? So if it is from FIQ, you don't want any other high priority because this one came first. You want to I mean perform or execute the instructions in ISR of this interrupt first. No other FIQ should be allowed. So you disable FIQs also. If this exception was from FIQ, you disable FIQ also. Because if it's not from FIQ, then you would want to be interrupted from FIQ because FIQs are the highest priority, right? So, but if it is from FIQ, then you want to settle this first. From FIQ, disable FIQ too. All right. So then your PC will get the vector address from the uh, PC will get vector address of the exception and the execution of exception will be performed. All right. So these I wanted to discuss this because this is slightly different from normal interrupts that we have studied previously. So that's yeah. So that is the exceptions. Uh, And why is FIQ fastest? Or how have the programmers or designers ensured that it is fastest? Just a little point that sir also mentioned.
Because it has a separate set of registers. Register.
It's like its vector address is last, so it has ample of space. I mean, there's the space that is available for to write down its ISR is ample, so you don't have to jump to uh, other memory space to ensure that you don't overwrite over other interrupts ISRs. Getting
Yeah,
like earlier, the way we had it earlier, let's say these are the locations. Let's say ISR of first, one of the exception is here, second is here. So if you have this much of space and your ISR might be longer than this space, so you have to write some jump condition, or here it is branch condition. You have to write some branch condition so that your processor goes to the other position to execute the exception routine, right? For the FIQ is last, so you do not have to worry about overwriting the other ISRs, because for this one you have to worry that you don't overwrite on the ISR of some other exception, because whenever this exception occurs, your processor will come here, and if you overwrite this position with the ISR of this one, so processor won't be actually executing the ISR of the second one, this is the first, right? It will start from somewhere middle of the ISR of first exception. So to prevent that, we write some jump conditions here. But for FIQ, we do not need to write the jump conditions because it has ample of space, and you can write however long your ISR is. Any questions on that? Okay. So has these different kinds of processes called cortex processes. They are distinguished, classified as cortex A, cortex R, and cortex M. So A is just your application processor. Your full OS is there. Cortex R is embedded processor for real-time signal processing, and Cortex M is more the kind of processor that we've been studying until now. So yeah, so we had Cortex A, R, and M. M is closest to what we've been studying. So starting with okay, then some I don't know. This then else if then else condition was different in this Cortex M processor that I mentioned. You can have these to three conditions the way you do in C programming, normal if else conditions. So that kind of instructions are present for the Cortex M processor, which is kind of a highlight. Then you have, why am I having this AVR timer here? I don't know. Okay. Ignore this one, okay? That's it for ARM processors. Moving on to, okay, we have more. Exception handling if then conditions are okay for Cortex. Okay, then we will start with the PIC microcontrollers. So PIC18 is a family of microcontrollers and normal microcontroller unit. Can you see the screen? I don't think. Yeah, now it's visible. Okay, so a whole unit of PIC18 microcontroller will contain microprocessor memory. Normally, the way microcontrollers have your I/O ports and your support devices like UART or other peripheral connections available. So that's for just a minute. Huh. So yeah, as you can see here, just by seeing the diagram, even if you don't remember, can you what do I say? Can you guess which architecture is it based on? Just by looking at the diagram. So up until now, you have studied two kinds of architectures, Neumann and Harvard. And how do they differ? The kind of memory space that you have for the microcontroller. For Neumann architecture, your program and data memory are same, like in single space. You programmer will have to see how it's going, he or how they're going to divide it. For Harvard architecture, you have separate memory space for program and separate memory space for data. Now, by looking at the diagram, which architecture does PIC follow?
ARM architecture,
Harvard.
Harvard architect. Yeah,
Harvard architecture.
Harvard, right?
yeah.
Yeah. So, PIC family of microcontrollers follows Harvard architecture, as you can see. Then you have memory. Yes. Okay. So, you have different memory space for program as well as data memory, right? And if you can see here, you have different address bus for program memory, address bus for data memory, data bus for or instruction bus for program memory, and data bus for your data memory. Now, and how many bits these buses are, they are also mentioned. So, can you now give me what is the size of memory?
Please repeat. Your voice was not audible.
Oh, I'm just saying that what is the memory space or range of memory locations that is available in the PIC microcontrollers diagram that is shown here. Like if you have a 21-bit address bus, what range of addresses can it access?
Uh, 2 MB access capacity.
Yeah, okay. So total memory that can be accessed is by 21 bit is 2 to power 21,
Yes.
right?
Yeah.
Which is 2 MB of space. Your data bus, which is 16-bit, can access 2 to power 16.
16. Yes.
No, wait, I have something. Okay, yeah. So address bus for data memory is 12-bit. So which means it can access 2 to power 12, which is
4 KB.
4
4 KB.
kbs of space. So just by seeing the diagram, uh, you can, I mean, know about the microcontroller, even if you don't, I mean, if you know, if you boil everything down into this diagram, you can remember everything. I mean, there's nothing to be remembered if you know what your diagram of the processor is or microcontroller is. Just wanted to show this. Then next thing is your registers, or if we are talking about buses only. So address buses give you the what do you say? Total memory space, right? What does data bus give you? I mean bits of data bus. How your memory is stored, organized, right? So if you have, let's say, for a program memory, you have 16-bit address bus, which means 16 bits of instructions can be implemented. So when you fetch or given instructions, write in instructions or read, the whole instruction can be of 16-bit max, right? I don't know. Are you able to understand?
Yeah.
Okay. So 16-bit data bus for your program memory, 8-bit data bus for your data memory, which means your data is stored as 8 bits. That's that. Then moving on to registers. So which one of the following is your accumulator? Just a minute. This working register name is changed, but this is your accumulator. This works as accumulator. It is 8-bit. Then in ALU, other registers you have status register and instruction decoders. Then your normal registers will have bank select registers, file select registers, program counters, and the whole thing has a control unit. Yeah, that's it for memory. And yeah, okay. So let's come back here only. So your program counter is 21-bit register, and your bank select register. Uh, what is the is a 4-bit register first of all, but as the name suggests, it is used to select the banks. So your memory is divided into banks, and your bank select register holds the address of the bank from which you are using the the bank whose registers you're using currently for the program execution, right? So bank select register BSR will contain the address of the data memory of the bank that you're using. Then you have 12-bit file select registers, which are just used as memory pointers for the indirect addressing. Then, yeah, so it has 16 banks. Uh, Total of 16 banks are there, and addresses of which are is in BSR, banks select register. Then all of these register, let's say this first register, this is the second one, this is the fifth. Uh, there are 16 banks, so you'll have one until F. No, one till F is 15, right? I don't know the name like that. Okay, so there's this one bank which is made up of first half of first register and second half of last register. So these banks, this is the first bank, let's say. This is from 00 to 0000 to 07F, 0FF. And middle of this
No,
is the address 07F, right? So this so this first half of first bank and second half of the last bank, they together make up a special bank which we call as Axis Bank. Okay. So the part which is coming from this bank is has the journal purpose registers, and the one that is coming from this last one is has special function registers. This is something special that about this memory allocation. Otherwise, I think everything is mentioned. What else? Okay, so yeah, that's your memory allocation. Then you have IO ports. In PIC, you have five IO ports. Each can be identified from its ISR, sorry, SFR. Each port has its own, can be identified or can be used using its SFR address, assigned SFR. Then your ports A and B pins are multiplexed. I don't have diagram here, but okay. Then your support devices. Okay, so you have uh, five ports, each can be identified by its assigned SFR address. Then pins or ports A and B. Mugs, they have multiple operations that can be done through them. Next. Then your support devices contain what or include what? Your timer, serial com pins, your analog to digital converters, your parallel slave ports, and data input. Data input. Then your special features, yes. So I think all of those you understood, but this one watchdog timer is one that I want to discuss. Your special features included watchdog timer, encode programming, encode debugging. So encode programming, debugging, you understand, right? While programming, while doing the execution of what you can program, right? Or debug. So this watchdog timer does what? Anyone wants to try?
uh, The watchdog timer actually is useful when we got some activity which is supposed to be complete within the time, but it is not. At that time, uh, we can use this. We can this watchdog timer is useful that time.
Yes, used. So important thing is what activity. So whenever, let's say, there's some system failure or anything, we want our system to be robust enough to take care of that failure, right? But let's
Yeah.
say your system is not able to regain its or prevent or get over the failure or get to the normal functioning in right time. That's where your watchdog timer comes into play. Okay, what it'll do is it's like let's say something happened, some failure occurred, and this watchdog timer will start the counter independent of your system clock. Okay, so what the way this works is the microcontroller will have to regain. Let's say there's a timer, there's this time limit up until watchdog timer will count up to, right? If it reaches that count, I mean, if it treat it as your normal timer, right? If it reaches its maximum count, no, your normal counter will stop there or will reload, right? So what watchdog timer does is it will reset your system. If it is not stopped by your system, it will restart the system itself.
Yes.
Okay. So yeah, that's it. So yeah, the motive is to automatically reset your system in case of any system failure, but with given amount of delay. That delay, it's not like always the failure will be like this that your system will need a reset. Sometimes system regains its normal operations, right? And for that, this watchdog timer is counting up until that time that you do whatever you can and try to correct whatever is wrong, but only up until I don't get to my maximum count. If I get to my maximum count, I will reset the whole system. I think
Yeah.
so. This watchdog timer is to let's say in order to get a robust system functionality, this is used. I'm writing this down here, okay? So it starts the counter, starts its counter independent of system clock, right? What happens is, uh, okay, so the maximum count is called timeout. So if software clears clears its timer before the timer, uh, it's, what do you say? Nothing happens. It just stops, okay? But if it is not cleared before timer, not cleared before timeout, it will reset the system. All right. And you preload the watchdog timer with the timeout period. I mean, you can decide by what time you want this to wait, and after what time your system will require a reset. Okay, you can be loaded with your timeout period. Okay. Hmm. So that's about watchdog. I hope it's clear. Then you have flags, which are somewhere here. So you have five flags. I think we discussed this earlier also. And negative overflow, zero, digit carry, and carry. Um, what else? There's this one thing. Yeah, I have a question, but let's just do it. If we should, can I erase this or do you want to write it? Or I can just use another page. Just a minute. Uh, okay, so regarding this flags, there's just this one normal addition that you will have to do. Let's add uh, 9F and 5 to hex numbers. Okay, and we'll see how they modify your flags. Okay, so 9F is what? 1001, 1111. 5 is 0101, 2 is 0010. So when I add this, what will I get? 1, 110, 0, 0. We have 1 here, 1, 1, 1, 1. So result is this, F1. Now I want to see how this operation affect the flags. Okay. So you have five flags: N, overflow, carry, digit carry. What have I left? Zero, right? Yeah. So can anyone or does anyone want to try? Anyone? Okay, let's do the easiest one first. Is the result zero?
No,
No.
No. So zero flag will be
zero flag would be zero.
zero. Is there an overflow?
No,
No.
No overflow. Zero.
it's zero.
Is there a carry?
No.
No, ma'am. So carry also
No
zero.
carry. Now what about this digit carry?
It is one, ma'am.
This is one because we had this carry, right? The digit carry
Yes,
will be one. And what about n?
yes. It's not negative. It's negative number, ma'am.
It's a negative number, so it will be 1.
How did you recognize it's a negative number?
Since its most significant bit is one.
Yes. So MSB
It's 1. That's why.
is when it is one. it's for negative. When it's 0, the number is positive. So, since here it is 1, the number result is negative, so your N flag will be 1. Right?
Yes, ma'am.
Now let's do one more. It's a bit different. I like the way this helps understand the flag. So, yeah, just that. So, let's add 9F and 72 now. Okay, 9F is same 1001 1111. 72 is 0 111. 2 is 0010. Right? Adding this will give you 1 0 1 0 1 0 1 1. This will be 0 1 0 1 0 and 1. Now,
One
in
one and one get
overflow insert. Yeah. First of all, the answer is 1 1. So the result is not 0. So
yeah
0 flag will should be 0.
zero yeah
There's a digit carry. So 1. The number
and
is negative
the
or positive
number is positive number, so n will be 0.
and will be 0. How about
Carry is
carry?
there. Yeah, one carry is there.
One carry is there. What about overflow?
Overflow is
It's overflow is there, ma'am.
both
It's
the cases.
It's one.
okay. When is overflow
No,
affected?
overflow will not be one. It will be zero, I think.
No, 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 no. The question is when is overflow affected? When when is your overflow flag affected? When the operation is between signed or
Addition of
unsigned numbers.
yeah
Signed numbers, right?
yeah
And these
sign.
are not signed numbers since I didn't mention them. So overflow should be 0. These are unsigned numbers.
Okay.
Okay. Whenever there's an operation between signed numbers and then there's the overflow. Overflow is basically your, let's say, if your range is from if your range is from -7 to 7 plus 7, I mean, it's just an example, okay? And your result is out of this range, then you will have something out of here, like you had a carry here. Yeah, I'm just explaining it that. So, whenever you have signed numbers, you'll have range like -7 to 7, right? Minus 7 to 8, I don't know. I don't remember. But let's say the range is this, right? And you have signed numbers. And whenever your result is, yeah, if your result is out of this range, you'll have something out like this you had carry, right? This carry was out. If this was signed, so you would have the overflow flag as 1 if the numbers were signed. If the operation was between the signed numbers, overflow flag would have been 1. But since the numbers here are not signed, your range is not out of your signed numbers range. That is why your overflow flag will be 0. It is affected only when operation is between signed numbers. Numbers. Okay, I like this one, so I thought I'll add this. Anyways, you can practice more questions like this, or if I find more, I'll add in the PPT. So these were flags. Then you have file select registers. Just that just like the memory pointers. And how many bits they were? 12-bit file select registers. Then some of the programming instructions were also discussed. Mhm. Yeah. So in total you have 77 instructions for PIC controller. Most of them are 16-bit word length, and four instructions are 32-bit word length. Then you did an example of eliminating alternate LEDs on some port. Let me see if I have other instructions. No. Okay. So I think that's it for pick. Hmm. Uh, no, one more thing. I think I have it in next. Yeah. So programming, uh, since now this is your, I think, fourth microcontroller processor that you're studying, you know what is the basic structure of all the programming, and I mean, you know it from your C programming, right? Only thing is, how the syntax changes, how you write. So, Pix programming is almost same as you have done in previous processes. Only difference that I wanted to mention was this the instructions where they have this LW, WF and FF. So, and it is going to be same for this is the moving content instruction example. Same for your arithmetic and logic instructions. I think I have it in my notes somewhere. Yeah, basically that's it. Okay, I'll just explain it here. I had some instructions for ARM also. Okay, we'll see about that later. But right now, so generally you'll have instructions like these only, like you know what move is, right? What is new is this LWWFFF. So here, L is for loading, W is for your working register. Are you able to see? Or should I write it larger? I don't know.
Yeah,
So
it is visible.
if you understand what this LMOV is, and you'll know what your instruction is. I mean, you don't need to remember it then. So this instruction move LW 8-bit. This can be any 8-bit number. This is immediate kind of instruction. So what you're doing here is you're loading an 8-bit number into your working register. This 8-bit number working register will get this 8-bit number, whatever you have mentioned in your instruction, right? So next kind of instruction is move WF F comma A. So if you remember from your earlier, let's say 8085, you had instructions like move A comma B, right? You had to mention that the operation is between accumulator and some register. Here, your instruction is you don't need to give an extra operand here. Instruction itself is self-explanatory to the processor that this moving of contents, copying of content is between this W and some file register, your working register and your file register, which is your memory. So this file register can be your whatever, R1, 2, whatever. Okay. So this much is sorted. Whenever it is LW, it is load with working register. I mean, this is not all of it, but this will give you somewhat idea of how the instructions are written. So yeah, so what this instruction is doing is copying the content of this register into your working register, and there's this one A. This is just one bit. You give it as 0 or 1, and if it is 0, then your F is in your access bank. Axis Bank, Axis Bank, Axis. Remember that bank that I told you about? That first half is from bank one's first
Bank
half.
one's uh, first half
This is
and
your GPR, yes. And this one is from bank
bank
F.
last bank second.
Oh, oh, bank. I'm not able to that. Oh, just a minute. Wait, I'm not able to that. It's not working. Okay, so whatever it is, this lower. How am I going to point it? Mm, Just a minute. Let me check. No, it's not working. But I can speak. So, okay. So this A will specify whether the band that is accessed is your access band or not. If it is 0, the bank will be this access bank where the upper half is from bank one's first half, lower is from SFRs from the last bank. Then you have, uh, yeah, so this is move WF instruction. Then move FF. Anyone wants to try what move FF is? The time, let me just taking cue from other instruction. What should move FF be? Anyone there? It's written there. So it's between one register to another register. So all of your instructions will be of this form only. Just pay attention and you'll get through. So that was pick uh, onto our fifth microcontroller. Okay, so these AVR microcontrollers are acronym for Advanced Virtual RISC Microcontrollers. Similarly, it has different data memory and program memory, so Harvard architecture. Instruction format, have we done it? Yeah, instruction format was I think is so it is 8-bit RISC architecture. It has these have 32 8-bit general purpose registers, and most instructions can be executed in one cycle, and these are designed for execution of compiled C code. So your level language, in you can code them in high level programming language, and these are available in different variants and depending on your size of flash, your program memory, size of your EEPROM, number of IO pins that are available, on-chip features, UART, and analog to digital converters. Yes, so they are high performance, low power, microprocessors, everything is done. Instruction is normally the way you had done, add RD, comma RR, and just it's not working. I don't know why. Okay. Uh, instruction is, let's say, add a RD, comma RR. So your first operand is both your destination and one of the sources. Like in previous microcontrollers in ARM, we had these three operands. Like you give R0, add A, add R0, comma R1, comma R2. Result is stored in R0, and the operation is between the contents of R1 and R2. Here, your ID is both your destination and one of the sources. So, yeah. Then there was this, ah, uh, let's say, I think it, okay, so instructions are, yeah, the 16-bit instructions, as it was discussed in class only. First 5 bits be the will classify what kind of instruction it is. Let's say you have add R23, R11, the same as taken in class. The first 5 bits will signify 5 or 6 bits. First,
5 bits.
uh, first five
Ze-
bits, yeah.
Yeah, yeah.
They
Zero is
signify
taken.
what kind of instruction. Sorry.
Zero
Okay.
is added with
So
that 5 bits that I'm telling.
five bits.
LSB.
So what kind of instruction you are giving in? Next will be for your register. Okay, so since you have 32 registers, how many bits do you need to specify? The number of the register?
5 bits.
So my hand is working, pencil is not working. Okay, I'll try writing with my hand then. Okay, so yeah. So if you have 32 registers, you'll require 5 bits to number them, right? So next five will be for your first operand, and the last five will be for your second operand. That's your ba the instruction format. Then your addressing modes. You had different kinds of addressing mode: register direct, register, yes, direct with two registers. Okay, register direct with one register, register direct with two registers, IO direct. I think they were explained fairly in class. So in register direct, you give just the instruction and one of the registers. let's say increment some R1 or R2, clear your R, or any kind of uh, arithmetic or logic instruction. Let's say you have XOR R. So it will XOR R, XOR R0 with R0 itself. Okay. Then you have register direct with two registers, similar as this add instruction. Then you have IO direct, in which you give one of the operands is some port spin. Okay. So yeah, that's the IO direct. One of the operand is from IO ports. Then you have data direct, in which you use, it's a 32-bit instruction. Uh, you give data from, since data will be 16-bit, and the other 16-bit will be for your operand and your source, or uh, yeah, your source or destination. Then you had data indirect, load or store instruct. You can have registers as pointers, and you can load or store values from these pointers. Let's say you have instruction like LD6, LD R16, comma Y. Y is some register which is pointing to some location. So this is like a normal indirect addressing mode. So value of the memory location to which Y is pointing to will be loaded onto this R16. Then you have data indirect with the displacement. Yeah. So yeah, these were the interesting instructions. So what happens is you give instruction and you give pointer and the pointer as the operand with some offset that you want to uh, offset for the location you want to actually use. So let's say Y is pointing to some location, but you want to access data from Y plus 2. So you give as operand Y plus 2 instead of incrementing Y first and then using it in the instruction. So this AVR processor will gives you that liberty because it has these kinds of instruction, data indirect with displacement, pre-decrement, post-increment. So yeah, these are similar kinds of instructions. With displacement, you just displace your memory pointer. Data indirect with the pre-decrement is you your I mean you decrement the whatever operand is given in instruction first, and then the operation is executed. That is pre-decrement. Then you have post-increment, in which the execution is done first, and then your value is incremented. That's I think that was where we ended. Then you had some special registers and counters of AVR microcontrollers. After that, oh, hmm, these serial interfaces. Uh, so these synchronous protocols, I don't think they were discussed. I don't know how much you understood, but from the perspective of your normal projects, even the small projects you do, this is really important because while designing your circuit or whatever system you're trying to do, so your data acquisition systems or signal processing systems, it is important to choose what kind of electronics you're going to use, right? So for that matter, it is important to understand these synchronous protocols. I think Sir went through them nicely. So just to recap, this SPI is serial peripheral interface. Nope. Okay, so SPI is your serial peripheral interface, and I2C is inter-integrated circuits. Uh, I don't remember, but you have studied them while we were doing serial, only the names were not used. You remember your full duplex and half duplex, right?
Yeah.
So, in that sense, SPI, serial peripheral interface, is your full duplex kind of system in which you have four wires and you can receive and transmit at the same time because of this uh, master out, slave in, and master in, slave out. You have two wires, two connections through which you can simultaneously transfer or receive data. So, which gives us, which, if you will remember, is the definition of full duplex system. And what else? And since it is a full duplex system, it is faster than your I2C. If you remember how Sir taught it, uh, then this SPI will have single master and can allow multiple slaves. Whereas if you remember in I2C, you have multiple master, you can have multiple masters and multiple slaves connected to just two lines. Since there are only two lines, I mean, here you have continuously four lines in SPI. Master out serial in, master in serial out, system clock and slave clock and slave select, right? But in I2C, you have only two buses to which all the masters and slaves will be connected. So it's a half duplex. You can at one time either receive or transmit data through I2C. And what else? It's slower, but it's used when you have short range, when you have long range transmission or reception taking place, communication taking place, because it is more economical, only two lines. For four lines, it will be costly in SPI's case. So there is a trade-off, whether you want fast or you want economical, as it is the case everywhere else. So both have their pros and cons. Yeah, that's it. That's what I wanted to say. Now, even if you do these small projects for your colleges, I don't know what kinds of project, 1 month, 2 month projects. If you use design these IoT circuits, you'll come across various chips and various electronics where not directly, but if you go through their pen names, you will be able to identify whether it's using I2C interface or SPI interface, and depending on that, you can choose which chips you want for your application. So yeah, just something to keep in mind. Yeah, that's it from the revision part. Moving to the practice problems, and not since they're not doing many programming problems, so practice problems are just what I've been discussing here, right? Okay, so which of the following modes in ARM does not allow modification of CPSR register?
User mode.
Anyone there?
User mode, is it?
Hmm. So user mode,
User
yes,
mode.
does not allow modification of CPI register. That answer is not working. Okay. Which ARM mode of operation is used by operating system kernel to perform privileged operations?
Supervisor
Uh,
mode.
supervisor mode. Just supervisor mode. Okay. Next is which of the following statements is true regarding BX and BLX instructions? X can be any of your conditions.
C. Option C.
Sorry.
Option C.
Option C.
Yeah.
Option C. Yep. Yes. Uh, okay. Next is which of the following statements is true regarding the use of 16-bit memory with thumb in ARM architecture?
Here also option C.
Not able to hear you, sorry.
Option C.
Really?
C. C.
If thumb is a 16-bit instruction mode and it is more power efficient, should 16 accessing 16-bit memory require more power?
No, it requires less power.
Not able to hear you. Can you write? You know, thumb is more power efficient mode, right? And C says that accessing 16-bit memory requires more power. That shouldn't be the answer if thumb is more power efficient mode, right? So thumb is more power efficient. First is the correct answer, first option. But just in case of any doubt, you can ask. All right. Next is in ARM 7. I don't think you'll remember it, but if you do, kudos to you. Vector address of IRQ interrupt is
Option D.
option.
D. D. 18. 1 8.
Yeah, option D. Uh, option D is correct. Then we have how many processor modes are available in ARM Cortex M series processor? I think I missed this. How many? So there are two modes, thread mode and handler mode. I don't think I discussed this. I don't have pencil to. I'll add this in the presentation later. Okay. So there are two modes, thread mode and handler mode. Thread mode is the normal standard mode where processor executes the normal program instructions. Okay. Handler mode is entered when it is entered automatically when some exception or interrupt occurs. Okay. In this mode, processor executes your ISR uh, and exception handler is used for execution. So two modes, thread mode and handler mode in ARM Cortex series, M series. Then which of the following registers is acts as a program counter in ARM Cortex-M series processor.
or 15.
R50. Hmm. Next is, what is the address bus size of PIC 18 for accessing data memory? Anyone?
12-bit.
Well, bit because it has 4 KBs of memory.
Accessing data memory. Yeah, 12-bit.
Well, bit 4 KB. Okay. Next is, uh, ah, so which company originally developed AVR microcontroller?
Atmel.
Atmel.
Atmel. Yeah.
Okay. So, how much in-system programmable flash memory is available in AVR microcontroller? I did not. Okay. So, 2 KBs of flash memory is available. I think I skipped this, but this was covered in your lectures, right? Next is, how many 8-bit timer modules are there in
One.
AVR?
One 8-bit timer module.
One 8-bit and one
16-bit.
other 16-bit. Right.
Yeah.
Next is, how many general purpose registers are there in AVR AP? Blah, blah, blah. So 32, we just discussed it, right?
Yeah.
32 general purpose
32
registers.
general purpose registers. Yeah.
Next is, what is the purpose of compare value? Okay, yes, I did not discuss this. I should have had. So, I don't know. This is not it. There are, I'll mark these. I'll add modes, and modes of area also. So, AVR has these three modes, normal mode, CTC mode, and PWM mode. Normal mode is just, in normal mode, it just counts up to maximum value and overflow. Okay, these are timer modes. Yeah, timer counter modes. It counts up to maximum value and overflows in normal mode. In CTC mode, it counts up until pre-assigned value by the user programmer and generates an interrupt whenever that value is reached and it reloads again. Okay, let's say the maximum value is from 00 to FF. In normal mode, it will go up until FF and roll over, not roll over, it overflows. In CTC mode, it counts up until, let's say, user has said count until 1F only. So it will count till 1F and then create an interrupt, generate an interrupt, and then it will overflow. Okay. Then there's third kind of mode, PWM mode, which is used to generate a square wave with variable duty cycles. Okay. So in this question, what is the purpose of compare value in CTC mode for timer module microcontroller? This is 14. It is to generate the interrupt when the counter reaches the compare value. This compare value is the value that is given in by programmer. Okay, it compares it to that value, and if they are equal, it will overflow. It won't go up until FX. Okay,
Yeah.
so B should be the correct answer. Uh, so what if it was normal mode, which would be the correct answer?
A.
A. just normally governmental effort, right? So, yeah. What are some of the applications for the timer module of AVR 8090S2313?
All of the above. D.
All of the above. Uh, all of the above. This is for your normal mode. This is for your CTC. And this is for your PWM mode. All right. So next is, what are the different modes of operation of, I just discussed them. So there are three modes.
D. All of the above.
D is the correct answer. Okay. So I think we have reached the end of questions. I had some instructions from ARM microcontroller. Just one or two things that I wanted to discuss. In ARM is the first one that we discussed. Okay, just in case you um, so normally all the instructions are okay. You have some additional instructions. Um, like normal move is like whatever move instruction you have done. Then you have MBN, in which let's say you have MBN R0 comma R1. What this instruction will do is R0 will get the value of not the value of R1, but one's complement of R1. Okay, so we have these kinds of instructions for ARM also. So very powerful kind of microcontroller. So just wanted to discuss that. Then you have normal add with carry, subtract, sub with carry or borrow, the way you like to call it. Then there's this one instruction. Uh, just a minute. Um, just the normal kind of instruction that like normally you have this subtract R0 comma R1. Now what this instruction will do, it will give the result as R0 minus R1, right? Whatever the result is, the result will be given by R0 minus R1 if the instruction is subtract R0 comma R1. And there's another kind of instruction, reverse subtract. In reverse subtract, what will happen is it will give the reverse answer. Like normally you'll have R0, if it is R0 comma R1, the result will be R0 minus R1. In reverse subtract, it's a three operand instruction. So RSB, R0, comma R1, comma R2. Result will be stored in R0. And in normal subtract, you will get R1, comma R2. Here you will get R2, comma R2 minus R1. And the result will be stored at R0. Okay, that's one. The other one is reverse subtract with carry. This is also applicable in subtract with carry or borrow. So what happens is subtraction will take place reverse, like if it is RSC R0 comma R1 comma R2. I don't know. I won't be able to write it. I'll add these later. Okay. So for this reverse subtract with carry, what will happen is result will be stored in R0, and what will be the result? It will be R2 minus R1 minus the complement of carry. Remember, in ARM of instructions, carry is generated in opposite way. If there is a carry, if there was a borrow, then the carry flag is 0, and if there was no borrow, carry flag is set, right? So for these kinds of instruction where subtract is to be done with the carry, I mean if the borrow was there, so complement of carry is has to be used. So this has, and this is done internally, so you don't have to worry about it. Just something nice to know. Uh, and one more thing, normally your arithmetic operations won't affect your flags for ARM controller, microcontroller. So if you want your, but this is flexible. So if you want your arithmetic operations to be affecting your flags, then you just have to add S with your opcode in the instruction. Like for add, for normal adding, add R0, R1, R2. For affecting the flag, you will have to write ADDS, adds R0, R1, R2. That's it. Yeah, I'll try to add these before I upload the PPT. But that's it from me. I'm done for today. Any questions? No? All right. Thanks, everyone. Thanks for joining. And please let me know if your question has been corrected or not next time. I'll see what can be done.
Yeah,
Yeah.
sure.
Thanks. Good night.